So worth it though. All right, section 10.4, compound events. We're going to start by talking about the sample space. So the sample space is the set of all possible outcomes. All possible outcomes of one or more events. We've talked about sample space already. We just haven't had a name for it. When you roll a number cube, what are the possible numbers that you could roll? 6 is one of them. 1, 2, 4, 3, 5. Yeah. So you could roll any of those. That's the sample space. When you flip a coin, what's the sample space? Heads or tails. Okay. So sample space, we don't really use it when we're talking about one event, but we use it when we're talking about 2 or more. Okay. So for example, if I was doing both of those things, I could flip heads and roll 1, flip heads, roll 2, flip heads, roll 3, flip heads, roll 4, tails, and all those options as well. So when we make a list of all of our possible options, that's the sample space. I will not tell you again, Natalie and Frank, to pay attention. I don't know what you're doing, but I'm going to take your iPad if it's not your notes. So one of the ways you can list that is with a table or a chart, or what we're going to do today is using a tree diagram. You can use tree diagrams to find your sample space. In fact, we'll use a tree diagram right here at this next question. It says you randomly choose a crust and then a style of pizza. Find the sample space, and then how many different pizzas are possible. So this is a 2-part question. Find the sample space, and then how many different options are there? So to find the sample space, we're going to use a tree diagram, and I'm going to list off, and I like tree diagrams because I can just use the first letter of the word. T stands for thin crust, S stands for stuffed crust. And so after I choose my 2 crust options, I can then choose one of the styles. They've got Hawaiian pizza, which we're just going to use an H for that. We've got Mexican style, pepperoni, classic, and veggie, which I guess would just be no meats, right? Be all the other vegetables. So I've got my Hawaiian, Mexican, pepperoni, and veggie. There are 4 styles for that crust. And then those same 4 styles I can use on a stuffed crust pizza. So stuffed crust Hawaiian, stuffed crust Mexican, stuffed crust pepperoni, and then stuffed crust veggie. So this is called my sample space. I've made a list or a diagram of all the possible options. How many possible options are there? There are 8. Every branch is an option. TH, or thin Hawaiian, is one style of pizza. Thin Mexican, thin pepperoni, thin veggie. There are 4 options for the thin crust, and there are 4 options for the stuffed. And that's a total of 8. Good job. Before I move on, does anyone remember, because we did this during success time. Do you remember how you could have gotten 8 without having to do the sample space? Jude?
Times the style by 2.
That's right. There are 2 options for crust, and there are 4 options for the style. And if you multiply that together, you'll also get 8. And that's actually taking us right into the next section, which is called the fundamental counting principle. The fundamental counting principle says that we can find a total number of outcomes using multiplication. So I'm going to abbreviate FCP as fundamental counting principle, and that says to multiply the outcomes of each event together. So if event M has M outcomes and event N has N outcomes, you're just going to multiply those 2 together to find the total number. And that works for events where you times where you have 3 or more events. If I have, for example, more styles of of meats and veggies for my pizza, I could multiply by bigger numbers and multiply by a series of 3 or even 4 numbers as well. Okay, so in this case, Jude's exactly right. You could get 8 just by multiplying the number of crusts by the number of styles to get 8 total. This assumes that you're picking one of each. If you're picking two different styles or picking two different crusts, or I guess you just couldn't pick two different crusts, that would change. And there's another thing that you would talk about in high school where you talk about combinations and permutations. And that'll be something that we probably won't hit on this year. I don't think we're gonna have time to hit on that. All right, here's another question. Find the total number of possible outcomes of rolling a number cube and flipping a coin. So let's start with the coin. If I want to list the sample space, I would start with H and T. What's H and T stand for? Heads and tails. Okay. When I roll that number cube, I have 6 possible numbers. I could roll, flip a heads and then roll a 1, flip heads and roll a 2, roll a 3, roll a 4, roll a 5, or roll a 6. And I can also roll those same numbers after I flip tails. Tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. This is my sample space. Anytime you're asked for the sample space, make a diagram or make a list. If you don't like tree diagrams, you can make a list. I like the diagrams because I can just do the letters and the numbers, and we know that H3 means heads 3. If you're just asked for the total number, and not the sample space, then you don't have to do the sample space then. You could just use the fundamental counting principle. How many options are there on the coin? 2. And on the number cube? And 2 times 6 is 12. And if you count them up, you'll see 12 options, and here they are. Heads 1, heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. There's 6, and there's 6 more. That makes 12. Tails 1, tails 2, tails 3, tails 4, tails 5, and tails 6. 12 different options on the sample space. At a sub shop, you can choose ham, turkey, or roast beef on either white or wheat bread. You randomly choose a meat and then a bread. Find the sample space. So I have to list all the different ways I can do it, and then how many subs are possible. So it's a 2-part question. If you want, though, we could actually start with the total number. How many options are there for the meats? 3 for the breads? 3 times 2 is, so the answer is 6. There are 6 possible subs. Now we're going to make a list or a diagram of what they are. Do you want to start by picking the bread first or the meat first? The bread, that's typically what you do like at a sub shop, right? So they both start with W. In fact, they both have WH as their first 2 letters. So I'm going to do WI for white and WE for wheat. Oui. French and English. What's we mean in French? Yes. And what's we mean in English? Us. Yes, plural. Yeah. Okay. Oui. All right. So you could pick a white ham sub, a white turkey, or a white roast beef, or you could pick those same 3 options on wheat bread, the wheat ham, the wheat turkey, and the wheat roast beef. And there are your 6 options. Now, it can be confusing because some people will look at that and they'll say there's 8 options because they're counting these 2. Don't count those 2. Count the entire branch. White ham, white turkey, white roast beef, wheat ham, wheat turkey, wheat roast beef. There's 6 total options there. That matches what we know we should get when we multiply 3 times 6. Now, if you go to a place like Subway, you're going to have tons of more options though, right? So not only do they have more bread choices and more meat choices, they also have tons of veggies and sauces and stuff you could add to it. So let's just say that there's I don't know, how many breads are there at Subway? There's flatbread, there's the white and the wheat, there's my favorite, which is the Italian urban cheese. Okay, so let's just say there's 4. And for the meats, I know there's like different combinations. So let's just stick with we can add chicken. They do have chicken. Let's just say there's ham, turkey, roast beef, and chicken. But I know that there's, when you order it, there's the chicken BLT and there's the cold cut, the Black Forest ham. There's different types of ham. We'll just say that. Vegetables. They've got the tomato, lettuce, onion, cucumber,
Jalapenos.
olives, jalapenos, banana peppers,
And then the normal
pickles,
peppers are like bell peppers,
spinach.
and then like sweet bell peppers.
We said the peppers already.
Bell.
Bell peppers, is that different from banana peppers?
Yeah.
Okay. All right. Okay, so there's 10. What about the, let's just say I had to pick one bread, one meat, one veggie, and then one type of sauce. So they've got ranch, they got mayo,
Buffalo.
they've got buffalo, they have buffalo now?
Yeah.
Okay, buffalo.
And then they
Someone
have
said like the sweet onion, okay, vinegar,
It's not pure vinegar. It's olive oil.
Western, yeah, the Chipotle Southwest, is that what you're talking about? Okay, olive oil,
I'm like a Subway.
that might be it, okay. Okay, so let's just say that we're going to increase our sub shop instead of having 3 breads and 3 meats and 2 breads to having 4 choices of bread, 4 choices of meat, 10 choices for veggie, and 7 choices for your sauce. That would increase our options from 6 subs to what? What's 4 times 4 times 10 times 7? Who's got it? Parker? 70? You did 10 times 7. Now times that by 4 times 4.
96.
No.
1,000.
1,120?
I just added 16.
Just by increasing, we gave 2 more options. We added the veggie and sauce option, and we increased the number of options, obviously, of the meat, the bread and the meat, and then lots of veggies and sauces to choose from. That gave us a 1,120 different ways we could make a sub. Imagine writing the sample space for that. No, thank you, right? No, thank you. So what I'm trying to prove to you is that this doesn't just work when you're picking 2 things. It works if you're picking 4, 5, 6 different. You just keep multiplying your options together. Find the total number of possible outcomes of rolling 2 number cubes. How many options are there on the first number cube? 6. And the second number cube? And that's a total of 36. We're multiplying. Yep, 36. In fact, when we did our dice experiment, when we did the first part on Wednesday, you listed the 36 questions, or sorry, the 36 outcomes right there. There were 6 options for the first dice. There were 6 options for the second dice. That gave you 36 different outcomes. Now, those 36 outcomes were not all unique. A lot of them repeated. In fact, we know 7 repeated the most. Then 6 and 8, then 5 and 9, then 4 and 10, then 11 and 3, and then finally 12 and 2 didn't have any repeats, right? So, but there was 36 different ways you could roll the dice. That's because rolling a 2 on the first dice and rolling a 3 on the second dice and getting a 5 is different from rolling a 3 on the first dice and a 2 on the second dice, even though you get the same outcome. It's the 2 different outcomes, 2 different ways of rolling that 5. Okay. In fact, this might be a good place to pause and show you guys the results of period 7's rolls. Okay. Okay, so the next question is number of, it's asking for the total number or how many different outfits you can make from having, picking out a t-shirt, a pair of jeans, and a pair of shoes out of your closet. So you're gonna pick one of each. Let's start with the t-shirts. Sierra, how many t-shirts are in that closet? Yeah, there are 7 t-shirts, okay. And Rayleigh, how many pairs of jeans are in that closet?
4.
4. Okay, good. And Hannah, how many pairs of shoes are in that closet? 3. So if you don't care about matching and you're just picking a random outfit together, everybody in here is matching. Well, pretty much. I'm matching, shoes matching. Okay. So if you are randomly picking your outfit together, you have 7 times 4 times 3 ways that you can make that outfit. Caden, what is that? You don't know 7 times 4 times 3 with a calculator right there by your right hand, the left hand? 84. There you go. Actually, you could have done it without a calculator. Now that I look at it, can someone explain how you could have done it without, Hannah? Yeah, that's right. You could have used the commutative property, which allows you to start on a different side of multiplication or an addition problem. You could have done 4 times 3 first to get 12, and then 12 times 7, because most of us know our 12s up to 7 to get 84. Okay. All right, total number of possible outcomes of spinning the spinner and choosing a number from 1 to 5. Branson, how many options are there on the spinner? 4. Okay. And Aiden, how many options are there from 1 to 5? How many numbers are there from 1 to 5? 1, 2, 3, 4, 5. Okay. I'll give you a second chance here, Aiden. What do you get when you multiply for our total number of options here? 20. Yeah. Now, notice on the last 2 questions, the reason we've just been multiplying is because they have not been asking us to find the sample space. This one wouldn't be terrible to find the sample space. You'd have to have red 1, red 2, red 3, red 4, red 5, then blue 1 through 5, then green, and then yellow 1 through 5. And so you could get your 20 options that way. This one would be a lot more difficult with the 84 options. Oh, I like these problems. Okay, you're buying a combination lock. You have 3 choices: lock 1, lock number 2, or lock number 3. We're going to find out how secure each of them are. So on lock number 1, it says this lock has 3 wheels. Each wheel is numbered 0 through 9. By the way, 0 through 9, how many numbers is that? 10, because you have to count 0 as one of the numbers. Right? 1 through 9 is 9, but then you have to have 0. So there are 10 options on that wheel. And there's 10 options actually on all 3 of the wheels. What's the smallest 3-digit number you can make with those options then? Natalie? There's 10 numbers in each one, 0 through 9. Yes, you choose one number for each. What's the smallest code you could have? 0, 0, 0. That's right. 0, 0, 0 is the smallest code you could have. And the largest code you could have? 999. With these 1-digit numbers. Yeah, 999. How many different numbers are from 0 to 999? 1,000, because you have to count 0. So from 1 to 999 is 999. Add the 0 option or the 000 option, and that's going to be 1,000 different ways. And there's an easier way to do that. Didn't you say there was 10 options on each wheel? What are we supposed to do with the 10, the 10, the 10? That's right. 10 times 10 times 10 is 1,000 different combinations. That's a pretty secure lock. I mean, someone could be trying up to 1,000 times to try to break in, unless you've told them the code or something, in which case they could eliminate a lot of their options. Yes.
Wait, why can't we count 0 if it's not doing it?
Because 0 is one of the numbers that you can select. It could do something. It could actually be part of the code.
Oh, really?
Yeah. There could be like one, or it could, yeah. So if someone, if you were setting this lock yourself, you wouldn't want to set it at 0, 0, 0, because that's probably the first one someone would try to check if they're going numerically, right? So yeah, I wouldn't start there, but 0 could be one of the numbers, or 3 numbers. All right, now we have lock number 2. It says this lock is numbered 0 through 39. Now, how many numbers are there from 0 to 39? 40. So you got to count the number 0, exactly. So this one's like your school locker, except your school locker, I think, goes to 49. This one goes to 39, so it doesn't have, but it has that right, left, right pattern. And so there are 40 different numbers you could have for the first number in that combination. And then when you go the other way, can a number repeat? Sure it could. So you have another 40 numbers you could choose from. And when you go the third way, there's another 40 numbers you could choose from. So what's 40 times 40 times 40? Shout it out when you got it. 64,000. That's right. Nice job. 64,000 different ways. And so which lock is the most secure now? Yeah, 64 times as secure as the first lock. There's 64,000 different ways. And I know you're thinking, well, there's the same number of turns, but now we're going, instead of 0 through 9, we're going from 0 to 39. And that's going to have a huge impact on our lock. Then we've got lock number 3, which has 4 wheels. So 4 numbers to multiply. How many numbers are there from 0 to 9? How many letters are there from A to J? 10. K through T. LNOPQRST. Another 10. And then 0 through 9 again. So this is going to be 10 times 10 times 10 times 10, or 10 to the 4th power is another way of writing that if you want to use exponents. Some of your calculators have an exponent button. Just do 10 to the 4th if you have a scientific calculator. What do you get? 10,000. Is it as secure as the second lock? No. So adding another wheel didn't make it more secure because it could only fit 10 digits or 10 numbers. Oh, sorry, 10 digits or 10 letters on the wheel. Now, a digit is a number, by the way, 0 through 9, and the letters are letters. But adding a 4th wheel still didn't come up anywhere close to the 0 through 39 that you could have had on each of the 3 wheels in the previous lock. So lock number 2 is most secure because that's 64,000 ways to set that combination.
I think it'd be hard to break into the orange block than it would be the block above it.
But you're wrong.
But like, that's just what I think.
You would think that going into it because it's got the extra wheel. I gotcha.
No, it's because that has like letters.
Ah, gotcha. I see. So the letters would make it more complicated. And then you realize there's really just 10 letters there, like there's 10 numbers on the other wheels. And so it would, yeah, 10,000 ways. I don't want to try breaking that lock, or breaking into it, but it's not as secure as the second one. Now your school locks, your school lockers go through 0 to 49. How many numbers is that? 50. So 50 times 50 times 50, who's got that? $125,000 different ways. So unless you tell someone your combination, they're not breaking into it. They are secure. Leaving something in your locker is secure. You just can't, again, you just can't tell someone your combination. Okay. Our next section is about compound events. And so everything we've been talking about so far is leading into this. A compound event consists of 2 or more events. So rolling a dice and flipping a coin. Instead of finding the sample space or just the total number of ways you can roll something, we are now going to look at the probability of rolling a specific thing. So for example, on this one, we listed the sample space for this one here. If I said, what's the probability of flipping heads and rolling a 3? Flipping heads and rolling a 3 was 1 out of how many different possible outcomes? 12. So you have 1/12 chance of doing that, right? Make sense? That's what we're going to do now. We're going to take it to the probability, which probability is fraction form or decimal or percent form. I shouldn't be getting an answer like 64,000 on a probability question that has to go from 0 to 1. All right, to find the probability of a compound event, we're going to use the fundamental counting principle to multiply our probability fractions together. We did this during that success time probability unit, and this was as difficult as it got. I said, this is as hard as this chapter gets, is multiplying 2 fractions together. So you roll a number cube, you flip a coin. What's the probability of rolling a number greater than a 4 and flipping tails? Let's start with the rolling a number greater than 4. How many numbers on a number cube are greater than 4? 2. 2 out of 6. What are those 2 numbers? 5 and 6, obviously. Okay. Now I know you can reduce that fraction, and I will in just a second. What's the probability of flipping tails? 1/2. So the fundamental counting principle, which tells me to multiply my options together, works with probabilities. multiply your probabilities together. And anytime you're multiplying fractions together, look to see if things cancel, like these 2's. You can cancel any top number with any bottom number, even if they're diagonal from each other. 2 goes into itself once, 2 goes into itself once. What's 1 times 1 on top? And 6 times 1 on bottom. That's your answer. So as you're showing your work on tonight's homework, there's questions that are going to want you to write the sample space. There's questions where you have to put like 3 times 4 times 7, which I know you can do in your calculator. Go ahead and write it anyways. And then there's problems like this where you have to multiply your probability fractions together to get your answer. What about the probability of rolling an even number? How many even numbers are there on a number cube? 3 out of 6. What are those numbers? 4, 6. And flipping a heads, still 1/2. Does anything cancel on this one? The 3 and the 6. Don't forget, you can still cancel normally, right? Top and bottom right above each other. The 3 goes into itself once, and the 3 goes into 6 twice. On top, what's 1 times 1? And on bottom, what's 2 times 2? There's your answer. And that's the lesson. We have some time. We can look at some homework questions. I've got a couple of them on here for you. And the first one I have on here is tonight's homework number 25. It says, you randomly guess the answers to 2 questions on a multiple choice test. I can't imagine you ever doing that. You study, right? You don't guess on answers. Now, this test only has the options A, B, and C. There's no D or E, okay? But you're guessing on 2 questions. So how many probabilities are we going to have? Hold on. How many times are we guessing? Twice. So we're going to have 2 probability fractions. Now, each fraction, it's going to be its own probability. So we'll say it's questions 1 and 2. Question 1, we're going to check it, see what its probability of getting correct is. And then same with question 2. So if we're guessing twice, we're going to need 2 fractions. What's the probability if the answer choices are A, B, and C that we get question 1 correct? 1/3. Yeah. Does everyone see how we get 1/3? 1 out of 3. Let's just say it's option A. Could it be option A for number 2? Really? Sure could, right? For option 2 could be A as well. I've had that on where, get 2 in a row. I question myself a little bit, but it could be. And so I have just the same probability of getting question 2 correct. So you have a 1/3 chance of getting number 1 correct. You got a 1/3 chance of getting number 2 correct if you're guessing completely out of left field here. That's a combined probability of what? Multiply 1/9. So the odds of you getting both of them correct are pretty slim. In fact, 1/9 as a percent, which is our next thing we're going to do, to turn a fraction to a percent, you have to do what, Frank? Divide. Frank, will you do 1 divided by 9, please? 0.1 repeating. Okay, so we're going to move the decimal over twice because that's what you do to change it to percent. What do I fill in with that empty blank right there? Another 1 because it's repeating, right? And then this one here is also a 1 because, the reason I'm writing that is because it wants the nearest 10th. So is that closer to 11.1 or 11.2%? Yeah, it's going to stay at 11.1. So you have an 11.1% chance of getting both questions correct. Better to study. Obviously, if you had more questions you had to guess on, that probability of getting them all right is going down, 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 down. Part B. Suppose you can eliminate one of the choices for each question, because sometimes you can. Like you've studied enough that you can say, well, I know it's not this guy. I know it wasn't this place, right? So let's say you could eliminate one of the options. So if there are 3 options and you could eliminate C on both of them, what's the chance of getting the first question right now? 50. Okay, so what is that as a fraction though? 1/2. And what's the probability of getting the second one correct now? Also 1/2 if you can eliminate one of the options. So we have a probability of 1/3 times 1/3 equals 1/9. Now that's going to change to 1/2 times 1/2 equals 1/4, which is option A, or 25%. Not 1/6, not 1/2 again. And being able to eliminate one of the choices does not, no, that's not, that totally affects. Process elimination actually is very helpful. All right, number 26. You forget the last 2 digits of your password for a website. Now that word digit does not mean letter, it means a number. It's a single digit number, and those digits are from 0 through 9, which is how many numbers? 10. So there's 10 digits you could put for, so let's just say this is your password, and then you forgot the last 2 digits. There's 10 options for this digit, and you can use the same number again, right? So there's 10 options for that digit as well. What's the probability that you randomly guess the first digit correctly? 1/10. I'll just use that as a fraction bar. 1/10. And what's the probability that you randomly guess the second fraction or the second number correctly? 1/10. So if you have 1/10 chance of getting the first of those digits correct, and then a 1/10 chance of getting the second of those digits correct, what's 1 times 1? And 10 times 10? You have a 1 out of 100 chance of getting both of them correct. You'd probably be locked out. Now, what is 1/100th as a percent? This might be the easiest question in the whole thing. 1%. What are all percents out of? So 1/100th is 1%. Now, if you turn it into a decimal, you're going to get 0.01, and you're going to slide it over twice, and you're going to be like, oh yeah, it's 1%. 1 out of 100, right? Okay. And we have time to actually surpass period 1 here for once in a while. Suppose you remember that both digits are even. How does that change the probability? So of the numbers 0 through 9, your even digits would be, I guess, 0, 2, 4, 6, and 8. Okay, so you went from 10 possible numbers to how many? Okay, so now you have 1 out of 5, and then 1 out of 5, which is 1 out of 25. So it increases your probability from 1/100th to 1/25th, which 1/25th is 4%, because there's like 25 like quarters, right? 25. So it's 4%. So you increase your percentage. It's like, wow, that should be a big increase. You go from 1% chance of getting both of them to 4% chance of getting both of them. Yay. You still need to know what they are. All right, we will do number 28 tomorrow and then start lesson 10.5. Have a great day. Get started on your 10.4 homework tonight, though. It is not due Friday, it is due Wednesday. You no longer have the homework due at the end of the day, just during iLearn week. So not at the end of the week, at the end of the, it's two days now.
No, say it.
Hi, I'm Mr. Bryce's class.
You're
Hi.
in Mr. Bright's class. All right, number 28, where we left off, says your model train has 1 engine and 8 train cars. Find the total number of ways that you can arrange the train. The engine must go first. So you have to, the engine is locked in to that first spot. And then it says there are 8 cars that you can arrange. So how many times am I going to be placing a car? How many cars are there? Am I using all of them? Yeah, so I've got 8 times. So I like to think of this, I've got 8 blanks is a way you could think about it. And then you've got the train, and the train's obviously got to go here. How many cars could I choose from to place right behind the train? I have 8 cars I could choose from, so I have 8 options. So there's 8, okay? Once I pick one of those cars, can I pick it again to go in the second spot? No, because there has to be a car in the first spot. If I've already chosen it, it's not going to be there again. So how many cars are there left for me to choose to go in the second spot? Okay, I just picked one. How many for the third spot? How many for the fourth spot? How many for the fifth spot? How many for the sixth spot? And for the seventh spot? And then when finally you get to that last spot, and there's only 1 car left, right? So the fundamental counting principle says multiply all of these options together, and you're going to get a pretty big number for this. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Frank? Say it again. 40,320 different ways that you could arrange your model train, with the train car going first and you selecting from the other 8 cars. That's a lot. Imagine doing a tree diagram listing all the ways that you could sort the cars, right? 40,000 plus branches. I would rather just multiply to find the number and not actually tell you all the different ways. Okay. Now, on your calculator, you might have a button on your calculator that looks like this, with an exclamation point. That exclamation point is called a factorial. And so what a factorial does is exactly this. It'll take whatever number you put next to the exclamation point, and it's not going to shout it at you like 8. Although it is kind of exciting because it will do the 8 times the 7 times the 6 times the 5 times the 4 times the 3 times the 2 times the 1, with all you having to do is hit 8 and then that button. Now, depending on what kind of calculator you use, getting to that button could be very difficult. If you have, not very difficult, but a little bit longer. If you have a calculator like mine, what you would want to do is hit the number 8 on your calculator. And then there is a button right here that says PRB. You hit that button, the PRB button. You see an option that says NPR, that's for permutations. We're not going to get to that this year. NCR for combinations. And then you see the exclamation point. To select the exclamation point or the factorial button, you have to hit the right arrow twice to where it's underlined. You hit enter, then it says 8 exclamation point or 8 factorial. You enter again and you get 40,320. Okay. These things get big really fast. 9 factorial, for example, is 362,880. Just by adding 1 extra car, I go from 40,000 plus ways to 360,000 plus ways. Right? Just by adding 1 extra car to my train and ways I can arrange it. Yes.
I 40,320.
Yes, that's the answer. You're a little bit behind.
Oh, no.
And you did it right.
Yeah.
So for example, when you put a batting lineup together, you typically will bat 9 people. And so if you had 9 players and they all batted, you'd have 362,880 ways that you could put your lineup together. Now, not all of them are going to be winning lineups, right? There's a strategy that comes to that, but that's a lot of different ways you could do that. Now, that's only if you had 9 players. Imagine if you had, 15 players on the team and you're trying to bat 9. Now the options are even going to get more. That's where the NPR option that you saw in the calculator, the NPR permutation, that's where that comes in handy. Okay. Combinations and permutations are basically all the different ways that you can arrange numbers or items where either the order doesn't matter or the order does matter. A permutation is when the order does matter. For example, your locker. If I told you the 3 numbers for your locker combination and you put them in the wrong order, would the locker open? So it shouldn't be a locker combination, it should be a locker permutation. One of my pet peeves. They keep saying locker combos, be like locker permo. I don't know what you call it, but it's a permutation, right? The order matters. A combination is when the order doesn't matter. For example, when you put a pizza together and you're putting toppings on the pizza, does it matter the order that you put the toppings on? Typically not. It's going to all get baked together, right? For the model train question we just did the order of the trains matter? Did the order of the cars matter, I should say? Once I placed one, could I place it again?
Yeah.
I could. So the order mattered then, right? The yellow car going in the first position is different from the yellow car going in the 7th position. Right. So then that's a permutation, not a combination. So you'll talk more about those in high school, and maybe you'll remember my exclamation point button on your calculator. Okay. Yes.
It's just like people who cut the lunch line. We're all gonna get to the same place.
Sure.